1 is equal to minus of h of 6. H of 1 is equal to minus of h of 6. Then h of 0, no, h of 0 is minus h of 6. H of 1 is minus h of 5. Okay. So this way it continues for asymmetric case. And at the center it is 0. Obviously it should be 0. So actually there are two driving equation. Okay, hn sine into alpha minus n into omega, and hn cos alpha minus n omega n into omega. So in order to have both of these two equations to be 0, these two accordingly impulse ratio should be. Now these are the definition of symmetric and asymmetric filter. Okay. Now we are considering case 1, that is when m is odd. Okay. So number of samples is odd, that is 7. Now for this again some mathematical formulations have been performed. So the Z transform is obtained in order to have the impulse response in Z domain Hz. So it is Hz is calculated. Once you get Hn, then Hk impulse response. Then in place of Z, okay, you just write the series, okay, and using the property, finally we get the this long equation. Okay. Equation number 1. Okay, this is very important in case of uh, in case of antisymmetric. Okay. Let me highlight it. So it is for m odd and antisymmetric. So z to the power minus m minus 1 by 2, h of m minus 1 by 2, and n is equal to 0 to m minus 3 by 2, and hn into this. So this is the antisymmetric for m odd case. There should be symmetric also. So here symmetric filter, this is the derivation should be there. I think, okay. Later on maybe it is given. So now yes, antisymmetric and m, no, it is m even. Yes. Then it is m even for antisymmetric. Okay, also this should, I should underline. This, and if a linear phase FIR filter, that is when m is even and antisymmetric. Then another is case 1, that is m odd symmetric. So in that case, m odd symmetric, the equation is this one. So you can understand if you go through all mathematical equations. So we don't have much time, but only this is important for the time being. For this moment in the online platform, okay, is very difficult. So we restrict to the important points, important formula. Okay. So now those those this impulse response AZ. Okay. So here they all exhibit the linear phase characteristics where theta omega, the phase term, okay, is equal to minus omega m minus 1 by 2, okay, or m minus 1 by 2 omega, that is alpha omega. So we have discussed alpha omega, that is theta varies as omega in case of linear phase. Theta, that is theta is equal to alpha omega plus alpha omega or minus alpha omega, where alpha is actually the center of symmetry of the impulse response. Okay. Sample number, the exact sample location. So here this is obtained from comparing this equation. Okay, you can see this equation have the magnitude and phase part. So this is the phase part and this is the magnitude part. Okay. So the phase part is, it tells that e to the power minus j omega m minus 1 by 2, and this is the magnitude part. Now from there we deduce that alpha is m minus 1 by 2. Okay. Now this hr omega, that is actually uh, the magnitude part or real part. Okay. This is this part only. Hr omega is this. So if you plot, okay, if you plot this, it is actually coming to be this kind of graph. Okay, this kind of graph. Now it has both positive magnitude and negative magnitude. Okay. So it is oscillating in between, but also it has positive and negative. So if you plot the phase characteristics, okay, then when it is negative, okay, that time it is seen that the phase pi is added, okay, with the previous phase angle. So omega m minus 1 by 2 plus pi. So this is shown graphically here, that if this is your phase response, this is your magnitude response. Phase response is actually when it is negative, that time phase is, when the phase is changing, it is changing by pi amount. Again, it is changing from positive negative to positive, again pi amount. So this way it is showing linear phase, but pi angle is added. Okay, theta omega is pi. Okay, when it is negative. So now for m even actually plot is slightly different. This kind of graph. So when m is even, okay, and there are many possible characteristics. Okay, we can have idea that uh, HR omega, if it is antisymmetric and m odd, then its magnitude part is this, and antisymmetric m even, this is this kind of graph. So to analyze this, you need to devote much time, and also mathematical analysis is required. Now, okay. So next another topic is windows linear phase. So linear phase filter, there was many techniques. First technique is the using that we discussed, that symmetric and anti-symmetric FIR filter, so that your impulse response would be such that it will provide automatically the this thing impulse the phase linear phase characteristics. Another technique is using window technique. There also we have to focus on the impulse response. Okay. Another technique was will be frequency sampling. There also you need to focus on impulse response. So in this method, using window technique, okay, using window technique, what is the uh, basic method, basic steps for window technique is, you see it is written that in this method we begin with the desired frequency response specification HD omega and determine the corresponding unit samples response HDN. Okay. So generally HD omega will be given to you, like if you will be like you will be asked to design one filter with some characteristics, with the given characteristics, so that from frequency range 0 to pi, this will be the phase, this will be the function, another range, this will be the function, another frequency range, this will be the functions. So this type of functions will be given, okay, to represent the frequency response of filter. Now, once this frequency response HD omega will be given to you, okay, then if you calculate the inverse Fourier transform of that given frequency response, okay, then it will come in time domain form. So if your desired frequency response is HD omega, in time domain, applying this equation 1 by 2 pi minus pi to pi, okay, this is actually inverse Fourier transform. So this will give you HDN. Okay. Now this will be the frequency impulse response or frequency response in time domain of the filter, okay, HDN. Now this will be in HDN will be what? If you find the integration, it will come in some function. So and it does not have any limit. It is not limited or restricted. Number of samples will be very high or infinite. So we have to restrict those the sample different samples of HDN into some certain finite numbers. Okay. So let us say HD after getting the inverse Fourier transform, if you get infinite number of samples and we want to convert it into some finite number of samples, so what thing we need to do is to multiply that function with a window function. Okay, HDN, suppose it is a sine function HDN and it is continuous, and not it is continuous, it is means number of samples is infinite. So you want to restrict to some say m number of points, so you need to have a rectangular window, okay, or any other window of length m. So this is called windowing techniques. So basic window is rectangular window. So your desired frequency response, okay, is HDN or inverse Fourier transform of frequency response HD omega is HDN. Now you want to limit to some finite length, so you multiply it with Wn, where Wn is the rectangular functions. It is not continuous, it is actually discrete. So, and that will give you the impulse response of that particular filter that we want to design. So Hn is equal to Hdn into Wn, where it is equal to Hdn for n is equal to 0 to m minus 1 and 0 otherwise. So now, so what we have done, we have multiplied two signals in time domain. One is HDN, another is WN, rectangular window, HDN and WN. So if you multiply it in time domain, what will happen? It will it will be convolution in frequency domain. So in frequency domain, we get the Fourier transform of that particular function, that is Wn. If it is your function, then frequency domain it will be W omega. Okay, and W omega should be convolved with the frequency domain representation HD omega, that is given, HD omega is given. So HD omega, so perform convolution between the desired filter characteristics HD omega in the with the frequency domain representation of that particular window, is W omega. So it will give you the impulse response in frequency domain H omega, that is given by 1 by 2 pi minus pi to pi HD omega W of omega minus nu. Okay, that is d nu. This is the formula for convolution. So this is actually continuous function. So we use the convolution formula for continuous signal. Okay, continuous function, not discrete functions. So that's why integration is used. Otherwise, summations would be there, would have been there. Now, let us do, if you take the rectangular function, okay, if you take the rectangular function, then as window function, so you calculate its Fourier transform. So its Fourier transform is W omega, okay, and W omega is, now use the discrete function, that is 1 into e to the power 1 for this many points 0 to m minus 1, and these are all 1. So 1 into e to the power minus j omega n. So it will be to the power minus j omega m minus 1 by 2. So this is the, finally we get e to the power minus j omega m minus 1 by 2 into sine omega m by 2 divided by sine omega by 2. Okay. So this has both magnitude and phase. So phase part is e to the power minus j omega m minus 1 by 2, and magnitude part is this sine omega m by 2 into sine omega by 2. So there you see that e to the power again minus j omega into alpha. Okay, that is theta omega is alpha omega. So there are also linear phase characteristics. Theta omega varies as omega. Okay. So and magnitude function is this. Okay, magnitude of sine omega m by 2 by sine omega by 2. So for that case, if you have this kind of function, this kind of curve, or frequency domain representation of rectangular function, okay, so if you plot these functions actually, so it will have some main lobes. It has main lobes and side lobes. Okay, main lobes and side lobes. Now, by suitable this assumption, okay, or suitable example, we can see that when sine omega m by 2 is equal to 0, okay, sine omega m by 2 is equal to 0, that time the main lobe, okay, main lobe crosses or main lobe becomes 0. Okay, that this one is 0. So that means omega is equal to 4 pi by m. So this omega at which the frequency, this is the frequency at which the function becomes 0. Okay, functions become 0. So we can say that the width of the width of the main lobe actually is dependent on number of samples of the window function. So if you take more number of samples, m increases. Okay, then that means it is a wide function. Okay, that is more DC value. So main lobe width will decrease. Okay, main lobe width will decrease. So so you can see that for M31, okay, width of the main lobe is higher than the width of the main lobe when number of sample is more, that is 61. So this concept you probably seen in case of analog communication, Fourier, when you studied Fourier transform. So whatever it is, so these are the this is window function. Okay, so this way the FIR filter is designed. So we can take one particular window, rectangular window, either in frequency domain or in time domain. If it is in frequency domain, if it is in time domain, then you your desired frequency response convert it into time domain. Okay, take the inverse Fourier transform, then you will get HDN, then you multiply the window function in time domain with that particular function, then you will get desired frequency response. And other technique is using convolution, and that is applicable for if you don't change the frequency domain representation of your desired filter, that it is already in frequency domain, then convert the window function into frequency domain and then find convolution. So there are two ways, either in time domain or in frequency domain. In time domain, it is better you just multiply those two functions, but in frequency domain, you have to convolve, find the convolution. Okay. And apart from this rectangular function, there are other defined window functions are there, like Bartlett. Okay, like triangular. It has triangular kind of impulse response characteristics. Blackman. Okay, you see that actually this all reduces the side lobes. Okay, one kind of apodization. You can tell this all reduces the side lobes. Hanning window, different versions are there. Now, one examples I have given that to design a symmetric low pass linear phase FIR filter having a desired frequency response HD omega is this. So this is your desired frequency response, and you have to create one filter that will have this frequency response. Okay, so first step is, what is the first step? Calculate. Let's say let it be in time domain. So you convert it into, you calculate the inverse Fourier transform of it. Okay, so that is done here, inverse Fourier transform. Then you have to multiply, okay, with rectangular window. So HDN is multiplied with rectangular window, that is WN. So if you multiply it, then you will get this function. Okay. Now one specific condition is there, that is explained, that n should not be equal to m minus 1 by 2, otherwise it will be 0 by 0, very high magnitude. So in that case, it will, the function hn should be slightly modified by using this formula. Okay, so sine x by x is equal to 1, assuming that sine x approximately equal to x when n tends to m minus 1 by 2. That is, n and m minus 1 by 2 are almost same. That time sine x approximately equal to x. So x by x is 1. Okay, so that's why it is approximated to, this can be modified by multiplying with, dividing and multiplying with omega c in the numerator and denominator. Then you will get omega c by pi at particular time instant m minus 1 by 2. And this actually occurs for m is equal to odd. For other case, it is not required. For m even, it will not arise. Okay. M minus 1 by 2 will not exist. So other some graph regarding number of samples, okay, is given. Some comparison, some characteristics are given. Okay. So you can see that as m increases, oscillation increases near band edge. For higher value of m, is more oscillation, and large oscillation is due to large side lobes of rectangular window. So if number of sample is less, then side lobe width will be more. Okay, so more bigger lobes are there. So that's why bigger lobes are there for less number of sample points. Whereas if you increase the number of samples, or if you consider the FIR filter to be more number of samples, that time the rectangular window has shorter lobes, side lobes. Okay, so that's why small oscillations, and this is called Gibbs phenomena. So to avoid this oscillation, generally other windows are considered. Okay. These are the other windows like rectangular window, Hamming window, Blackman, Kaiser. Okay. So you see that what is the advantage? That here 20 dB loss, okay, 20 dB, the stop band attenuation is very high, 20 dB for one case. Okay, rectangular, it is not that much high. Hamming window, it is very high, 60 dB. Black band, it is more high, 80 dB. So these are the standard window that are used for filtering. Then one numerical is there, that is design an FIR linear phase digital filter. Okay, with this omega is less than pi by 6. So you try to perform this one. Okay, and another next topic is frequency sampling method. So that I will explain tomorrow. Okay. So I now stop today. If you have any doubt, you can ask. If you have any doubt? Okay. So I am already uploaded, just go through it. Okay. And uh, probably yes, so I will take the class tomorrow. Okay. So you can leave now.